Hello friends, welcome to lecture number 15. In today's class, we'll read about capacitors. Okay, so to start this chapter, I give an example. All of you must have seen a Kodak camera. In the Kodak camera, probably we put 4 batteries to work, right? And that camera is having a flashlight, okay? So you see, at times when the flashlight goes, a huge amount of light is being given to you. Now, for that flashlight to run, the energy provided by the 4 batteries is not sufficient enough. So who provides the excess amount of energy required for that flashlight for a very small interval of time? So that job is done by capacitors. Okay, so basically these capacitors provide a huge amount of energy for a very short interval of time. So they are storehouses of energy. The second example I can give of that of the ceiling fans. You might be must have seen in many houses the fan doesn't work. So what they do is they will take a stick, try to give some initial rotation, and after that the fan will rotate. So what is happening? The capacitor which is there in the fan, that is not working properly. What is the job of that capacitor in the fan? To provide the initial rotational motion to the fan. Okay, so this is what is the job of the capacitor. So let us define this. What are capacitors? So we can define these capacitors as it is an energy storing device, which stores energy in a finite distance. So this is the definition of a capacitors. Okay, the second term which is of importance is your capacitance. Okay, now what is capacitance? Capacitance is the ability of a conductor to store charge. Okay, or you can say capacity to hold the charge per unit potential. Okay, so let us try to understand. We have a conductor. I have a conductor here, and to this conductor I give a charge Q, okay, for which a potential V is being developed. So the capacitance is denoted by C. C is your capacitance of the capacitor. C is equals to Q by V. Okay. Then what will be the unit of the capacitance? The unit will be coulomb per volt, which is called as farad. And there are many common units which will be required while solving problems. 1 millifarad will be equal to 10 to the power minus 3 farad. Okay, then you should also understand 1 microfarad. Micro is represented by mu. 1 microfarad is 10 to the power minus 6 farad, and 1 picofarad, small pf, that means picofarad. Pico is 10 to the power minus 12 farad. Okay, so after units, then let us go to what is the dimension. What is the dimension of capacitance C? So we know C is equals to Q by V, and potential is nothing but work done per unit charge. So Q square by W. Q square means, Q square will be there. Work done can be written as force into displacement. So Q square means it will be A square T square divided force is mlt minus 2. And what about the displacement? L. So the dimension of the capacitance C will be how much? It will be m to the power minus 1, L to the power minus 2, T to the power 4, A to the power 2. So this is the dimension. Okay. Then there are few points which are noteworthy for capacitance. Okay, the first point is your capacitance C does not doesn't depend doesn't depend on Q and V. Okay, rather it depends on the dimension of the system. Okay, in order to explain this point, I will give an example. In in class 10th you must have studied your resistance is V by I, which is also equal to rho L by A, resistivity. Okay, so it is very well known that R does not depend, it does not does not depend on V and I. So it depends on what? It depends on your R depends on whom? Rho, L and A. And these are nothing but these are the dimensions. These are the dimensions of the system. Similarly, you will see in our subsequent class, the capacitance does not depend on Q and V, rather it depends on whom? It depends on your dimension of the system. Okay. The second important point for capacitors are your capacitors are actually are actually instantaneous energy providing devices. Instantaneous energy providing devices. Okay, so these are the two things which you should always keep in your mind for reading capacitors. Okay, now after this let us take the initial capacitor as a sphere and find out its capacitance. So we'll give a heading capacitance of a sphere. Capacitance of a sphere. So what we do is we will take a sphere of radius r and we'll try to find out what is its capacitance. So I take a sphere of radius r, okay. Now what you give a charge q to it, so the potential developed will be how much? K q by r. Okay, now we know that the capacitance formula is q by v. So q divided by v. V is how much? K q by r. Okay, so this q gets cancelled out. So you have got r by k and c will be equal to finally 4 pi epsilon naught r. And you could easily make out your capacitance is proportional to r. And what is r? R is the dimension of the sphere. R is the dimension of the sphere. So basically the statement what I made here, that it does not depend on q and b, rather it depends on the dimension of the system. So it is clearly visible in case of sphere the capacitance depends on the dimension of the system and the dimension is r in this case. Okay, but whatever you found out here, it will come with two drawbacks. Actually the capacitance which you have found through the of the sphere, it has got two drawbacks, two negative points. Okay, so what are these negative points? Let us see. The first negative is, suppose you consider earth. We usually consider earth as a sphere. Okay, and what is the radius of the earth? It is almost 6400 kilometer. So what the scientists did, they put, suppose I take it as equation A. So they put the value of r in equation A. So once you put the value of r in equation A, then what is the capacitance? The capacitance was not equal to 1 farad. It was less than that. So it's better to write that the capacitance was less than 1 farad. So could you imagine, if I want a capacitor of capacitance 1 farad, then I have to construct a sphere which is bigger than the earth. Is it practically possible? Is it practically possible? So not a good solution, I would mention here, not a good solution. Okay, so this was the first drawback, that was the dimension. Okay, what was the second drawback? The second drawback was the energy in the capacitor. It was spread from R to infinity. Now suppose, to explain this, I'll take a very small example in day-to-day life. Suppose you want to drink water, and what I do is, there is a table in front of you. I take a glass of water and I pour the water on the table. Can you drink it? Probably not. You cannot drink it, right? So the water which is present in the on the table is of no use to you. Now if I collect that water inside the glass and give it to you, it is useful because you can drink it. Okay, so when the water was confined, then it was useful. When it was spread out, it was not useful. The same case will be applied here. You see, the energy is spread from R to infinity. Okay, that is what? That is, your energy is scattered. The energy is scattered. Okay, and we need to, when once we need to use it, we need to confine we need to confine the energy. Okay, so all of understood. First drawback was the dimension was the drawback. The second drawback was the energy was scattered. Okay, so what is our objective now? Our objective is the energy which we get from the capacitors, that needs to be confined in a smaller area. So our objective now is to confinement of energy in a smaller area, so lot of research went on, and finally they came to a capacitor which was called as your parallel plate capacitor. Okay, so this was very useful for us, and we will read in detail about this parallel plate capacitor. Okay, so before I get into this parallel plate capacitor, there is a very interesting question which usually comes in the exam, and we have to solve it. So it is given that there are two plates here, plate number 1, plate number 2. So in plate 1 we have positive charges, and in plate 2 we have negative charges. The question is, there are 3 points, point A, point B and point C here. So it is asking, what is the electric field at point A, electric field at point B and electric field at point C. We need to find out. Okay, so you see here, this is all, remember one thing, this is all about your lines of forces. It is quite obvious, at point A your electric field due to the first plate will be along this direction, E1, and E2 is along which direction? Is along this direction. Now what is E1? E1 is sigma by 2 epsilon naught. What is E2? It is same as that of sigma by epsilon naught, but the direction is opposite, magnitude is same. So what will be EA? 0. What about at point C? Your E1 will be along this direction and E2 will be along this direction, magnitude by same, direction opposite. So what will be the electric field at point C? It will be 0. But the interesting thing happens inside or in between the two plates at point B. What happens? Your E1 is along this direction and E2 is also along this direction. Therefore EB will be how much? Sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is equal to sigma by epsilon naught. So from this problem, one conclusion you can make, that the electric field between the plates of a capacitor is how much? It is, capacitor is sigma by epsilon naught. Okay, so now we will go to derive the expression for capacitance of a parallel plate capacitor. Okay, for that what we need to do? We need to take a parallel plate capacitor. Chalo, let us take a parallel plate capacitor here. we will take a parallel plate capacitor here, like this. Take like this. Now one of the plates is positive here, okay, positive, the other one is negative, okay, plus Q and minus Q. And what is the electric field between the two plates? Just now I calculated sigma by epsilon naught. Okay, the distance between the two plates is small d, and the potential difference between the two plates is V, right? So what I can take here, that your small d is the distance between the plates, okay, and what is V? V is the potential difference between the plates, and capital A will also be used. Capital A is area of the plate, okay. So now let us go on finding the capacitance. We know capacitance is equal to charge per potential, okay. Let us give it as equation 1. Now we also know that your V is equals to E into D, okay, and your sigma charge density, okay, surface charge density will be Q by A. So let us put V is equals to E into D, and what is the electric field between the parallel plate capacitors? We have just now calculated sigma by epsilon naught into D, and what will we put for sigma value? Q by A. So Q D by epsilon naught A, okay. Now you got the expression for V. Let it take it as equation 2. Put equation 2 in 1. So what we have, the capacitance Q divided by QD by epsilon naught A. Q gets cancelled out. So what is the capacitance? Epsilon naught A by D. So here also you see the capacitance depends on the dimension. Here also the capacitance depends on dimension, which we have mentioned earlier, okay. And what is the dimension here? That is area of the plate and the distance between the two plates, okay. So this is a very important derivation which comes for 3 marks to find out the capacitance between the parallel plate capacitors, okay. Now few points which are noteworthy, let me discuss those, okay. You can write notes. Here the first point of discussion is, now you see the energy which was spread out in the previous case in that of a sphere is now being able to be confined within a smaller region. So we can, the first thing can be the energy is confined within a small region. This is one of the biggest achievement, because if we confine it, then we can use it. The second one, by modulating the ratio, A by D ratio, okay, we can find or we can achieve large capacitance, okay, right. The third one is a very vital one which we should know is, if you see that if I ask you what is the net charge on the capacitor plates, plus Q and minus Q, so the net charge on the capacitor plate is always 0. So we can say the net charge on the capacitor plate is how much? Is 0, plus Q plus minus Q, okay. But we find that the electric field is not equal to 0 at this point, right? Then how the electric field lines will be between the two plates. Suppose you have a plate like this, right? This is plus, this is minus. You will get fields of this manner. You'll get fields of this manner. Electric field lines will be of this manner. Okay. Now the question comes, why is it so? Right? It was observed that the electric field is uniform. The electric field is uniform central in the central portion, okay, and non-uniform at edges. Okay, so this effect has got a name. This is called your edge effect. Okay, or it is also known as fringing. It is also called as fringing. Okay, very very important terms. Now this non-uniformity of electric field at the boundaries. So I would like to say one point here. What the students do, if the two plates are given, they will draw lines like this. This is not to be done starting from here to here. Okay, don't do like that. The yellow color ones are the correct ones. You have to draw it like this between the two parallel plate capacitors. Okay, the electric field lines. So what I can say here is, this non-uniformity of electric field at the boundaries of the plates become negligible. They can be neglected, becomes negligible when, what is the condition? Negligible. Okay, when distance between the plates is very small. Okay, compared to whom? Compared to the length of the plates. Okay, so I hope this is clear to you. I will just do two minute problems which are having high probability of making mistakes by the students. So what I do is, I take two rectangular plates of this manner. I take two rectangular plates of this manner. The distance between the two plates is C. The length is B, and here it is A. Okay, then what will be the capacitance? The capacitance we know, epsilon naught A by D. What is the area of the plate will be here? Epsilon naught A into B divided by, what is the distance between the two plates? C. Okay, so this is the capacitance. The second common question is, suppose I have got two spherical plates of radius r. Okay, circular plates I will have of radius r. The distance between them is d. Then what will be the capacitance? Epsilon naught A by D. And what will be the area? Area is pi r square divided by d. So this will be your capacitance. Okay, so this is it for today's class. I hope everybody must have liked the video. Do share it and do not forget to subscribe it. Any queries you have, you can mail me in the mail ID which is shown below. Finally, thank you for your kind patience.